Uh, so good afternoon, everyone, and a very warm welcome to the Statistics and Probability Seminar of the School of Mathematical Sciences here at the University of Nottingham. And because we do have a few people from outside, and I'm pretty sure they probably don't know me. So my name is Basir Rahman Kudabaksh, and I'll be hosting the seminar today. Our speaker today is Dr. Yordan Raykov. Yordan is a good friend and a colleague of mine here at Nottingham Maths. He's an assistant professor within the Statistics and Probability section. He's also affiliated with the Horizon Institute for Digital Welfare. Yordan holds a PhD in machine learning from Aston University, where he worked on scalable Bayesian nonparametric algorithms. But not just the methodological work that he's interested in, he's also interested in real applications. And I guess we will hear a lot about them today. So we're really looking forward to your talk, Yordan. Please go ahead.
Thanks for the introduction, and hello, everybody. I'll apologize ahead of the talk that initially it was planned to be with a different title and a bit more mathematical, and instead I'll have to go ahead and give you a bit more applied run-through. At any point, like if you want to like ask questions or ask something about algorithms or things like that, just break me as I talk, and we can like dive into specific details. Can you all see my screen?
Yes.
So while we talk, like I was planning on pulling out a bit more statistical challenges, but instead I'll give you the talk we sort of like spoke with to Parkinson's UK a couple of months ago about the roadmap of getting digital technology and wearables into clinical trials, which for the first time had started over the last year, and a lot of it is due to some statistical advances and statistical methodology, which is being adopted in place of more black box algorithms. So the sort of like one of the milestone studies that we used to develop this is what I'm going to present this today. It's called PD at Home, and it's all about using how do we use wearables to informally to bring extra information in clinical trials. So the primary objective is to design and assess algorithms for the analysis of wearable sensor data, where we're going to be mostly looking at passive real-life conditions. So we've developed a couple of applications in the last couple of years, which are all available on App Store and Android Store, and people download them directly from there in large-scale clinical trials, some of which are a few thousand people. Now, in order to train algorithms and see how they'll perform on this out-of-sample testing environment, we actually had to perform a fairly expensive study where these apps were downloaded, and we visited people with Parkinson's disease, and we took video recordings of them. So these were continuous feeds, so they were expensive, so they were on a smaller cohort of 25 Parkinson's patients and 25 controls. And we had people visiting these people. We monitored them for about more than 3 hours per person with a video camera. And then we had all sorts of traditional medical measurements collected, and then 2 weeks follow-ups where they're monitored more softly via online questionnaires were also performed. The main objective of what we're trying to do is to locate real-life gait and other real-life symptoms of Parkinson's disease to try and quantify the effect of Parkinson's disease, particularly on the gait pattern. So you're going to see that this is a lot more involved than just detecting walking or detecting a symptom of Parkinson's, because a symptom might have a lot of fluctuations, which you haven't necessarily seen during training. So what we're going to be dealing with is shifts in the test distribution, where the test distribution is very different from the training one. And we're going to be looking at, obviously, locating reliable variations of tremor as well. And this is because a recent survey showed that tremor is the most troublesome symptom of Parkinson's disease for Parkinson's patients in the first 5 years of their disease. So it really affects their quality of life. So the study timeline of particularly PD at home was we did initial pipeline development, which took about, which has these home visits of 3 hours of unscripted activities where people just go about their lives and someone tracks them with a camera. So admittedly, it wasn't great experience for the patients, but it was very useful for us. And afterwards, we had like a 2-week follow-up in which people are wearing wearable devices like a smartwatch and a smartphone as most ubiquitous. We collect data 24/7 in this period, and then we have like only a little bit of labeled information where we ask people to fill in a questionnaire of how they feel throughout the day.
Okay.
There's been also many related studies which can help us study the primary objectives across like around study evaluation, building context-aware knowledge, less biased models, and things like that. So we have leveraged actually a couple of other studies like that in order to train our algorithms, construct causal diagrams of what is it that we're looking after, and things like that. So first question that you might be wondering, if you're not familiar with the problem, is why would we go about passive monitoring, and what does passive monitoring means? So less formally, passive monitoring means that your device is collecting data continuously. Now, this is what your device is doing in any case already. It's just this data is rarely being used outside of the manufacturer, which is Apple, Google, and the big tech companies. So this is what we mean by passive. But this is not where wearable technology started. So over the last 15 years, the dominant approach of measuring disease using smartphones, and it has become a big thing if you're not familiar, has been you develop an application inside of the lab. So for example, you go into any media lab, the leading ones are MIT Media Lab and a couple of others. You develop a prototype application, which you think that might be recognizing Parkinson's patients from non-Parkinson's controls. This was one of the first Apple applications, but now there's also one for hepatitis, for Alzheimer's, and for many other neurological and motor disorders. You get quality sensor data. You develop it in the lab, but then you hope that this algorithm that you've trained inside of the lab on the perfect data, a couple of patients you've invited, is going to work outside. And over here, I've sort of like pointed out some of the challenges of why you might think that this is not going to be happening quite often. So getting quality data outside of the lab, which matches the distribution of the training data, is hard. So you get the patients that are better conditionally, and the patients that know how to have well-expressed symptoms quite often are more likely to attend these studies. And you actually don't get the challenging cases inside of your training data when you're training the prototype algorithm. Also, you have fairly small amount of data that is collected in the lab. So for the first Parkinson's application, we had 50 participants with Parkinson's and 50 without. And our test data set of where we were evaluating the platform was of 65,000 people. So you're hoping that an algorithm trained on 100 people is going to work well on 65,000, just to give you a perspective. There's also a lot of biasing activities which are unimportant to the application and decrease the inference performance and the quality of your diagnostics. So anything that goes wrong during these active tests in this limited period of time is going to affect your ability to tell someone whether they have Parkinson's or not, whether they're taking their medication or not, and it's impacting real people's routines. And finally, probably most important, is that you're going to be tempted to deploy black box machine learning algorithms for analysis of data like that, to train some black box classifier on 100 people, code up the application, deploy it, and then you have but the problem with that is that you have no idea out of sample, what is it doing? Is it really looking at the right symptoms? Are there adversarial examples? And why is it saying that this person has the disease and his disease is getting better? And this is not something that the FDA would accept as a viable tool. So I'll be only talking about Parkinson's disease because this is where my background is, but of course a lot of the algorithms extend to, and we've tested them on some other disorders as well. So diagnosing Parkinson's disease has these three main tests, which are quite popular by now, which are adopted in clinical trials as well, which are the topic test, a voice test, and then a motor test. So the basic protocol that a user is required to follow is they perform a specific test on a smartphone unsupervised at home. The first test is you're asked to tap a screen 20 times with your left and right finger. And depending on your patterns, you can sort of like detect something about the dexterity in the arm. The second one you're going to hear shortly is the voice test, where someone needs to say a vowel phonation to the microphone for 20 seconds. And the third one, someone is asking to walk around, like make 20 steps and make a turn. This is in principle, and this is what people have done indeed in the lab when in the original 100 people we collected over 7-8 years ago. And a clinician is then going to assess the quality of the collected data. It's going to compare it to the ideal collected data in the lab. They're going to pre-select the perfect recordings, train an algorithm, and every time an algorithm is tested, it's either tested on noisy data, or people are being paid to go by hand and annotate this data and remove everything that looks bad. To essentially by hand match the test distribution to the training one. Now, I brought in a couple of examples just to show you how bad this can be. It's the easiest to see in the voice test. So here people were asked to do 20-second phonation, but this is how 3 example tests from the real life homes actually sound like. Can you hear it?
No, actually, Yordan, I think you have to allow audio or share with audio that setting.
Yeah, sorry about that. So. So this is a good test, which starts well, but then afterwards, just the person cannot hold it for 20 seconds, which is already quite a predictor, actually, of the quality of the person's voice. Now, this is probably a worse example.
Into your ear, take a deep breath and say "ah" at a comfortable and steady tone, and over for as long as you can.
So this is quite a realistic recording where the person, an older person first reads the instruction to himself out loud, and then performs the test for shortly, and then there's like some background noise at the back. Now your ideal algorithm should be able to essentially ignore the irrelevant bits and focus on the phonation, and then from there tell you if you have Parkinson's disease or not, but it doesn't essentially. Sorry, and that's the final. Which is a typical example of people trying to toy with these tests. With the motor test, we get people putting their wearables on their pets, performing the tests in all sorts of weird ways, essentially try to fool your system. And whenever you're thinking about designing a robust system, you need to build in algorithm capability that fights for that. But now to make the challenge even worse, so here you could see at the top, these are the perfect walking tests, should look like that. So this is highly periodic time series data, where most of the information about people's walking, I'll talk about this more in detail, is in the spectrum of the time series. But majority of the time, a lot of the time at least, you get people to walk for a little bit, and then they might get Parkinson's irrelevant stopping of the gait and just stopping of the activity, or Parkinson's relevant walking, which is the so-called freezing of gait. Now, if you ignore the freezing of gait, often you can't necessarily say that someone has Parkinson's from their walk. But at the same time, if you include all the noise and intentional stops, then your test is useless. Now, to make the problem even worse, after a couple of years looking and designing algorithms that try and fix these recordings, we realized that we need to be moving towards passive monitoring of daily life anyway, because we cannot say much. We can say if someone has Parkinson's disease or not from a snippet of 20 seconds, but without a continuous view, we cannot say if they're getting better or worse. And what we really wanted to do is develop a system that tells you, are you getting, like, how is a new medication having an effect on your Parkinson's disease or not? So to have an insight into the real function of life, we need something that collects continuously data throughout the day. Now, to do that, we went about phase 1 of the home-based visits of the Parkinson's at home study, where we were aiming to learn how we can reliably monitor gait and tremor. And we're going to be doing this by developing some Bayesian nonparametrics graphical models. Then we studied different devices and built some generic probabilistic model framework for segmentation of different gait states, of different tremor states, and training them robustly using some novel robust MCMC ideas. And then we went about thinking, is it feasible to track levodopa-induced fluctuations in real life using wearables? And we did some evaluations of what is the best we managed to do using probabilistic modeling. So as I said, the study setup is that we have multiple sensor modalities. So we're collecting accelerometer, gyros, magnometers, everything that it's in a ubiquitous wearable device. And we have multiple body locations because we want to see whether the perfect body locations, how bad or worse are they in the quality of data as compared to the ones that we know that everyone uses, like a smartphone or a smartwatch. And we instruct patients to emit morning intake. So we simulate the levodopa withdrawal to see what do you look like, what do you behave like when you don't take your medication. And then you take your medication and collect some more data to have data from both before and after medication. And then there is a video recording that it's used for all the analysis we're going to talk about. Now, our objective is essentially over here. So even though there are lots of things that are happening in passive monitoring, and this is going to motivate a lot our model choice when we get to modeling, we need to ignore most of it, because most of what's happening in free living is just you're brushing your teeth, you're going to work, you're going to sleep, things that are fairly irrelevant, and they happen for both Parkinson's and not. And we need to focus on the things that are relevant for PD. So this has motivated the choice of gait and tremor. The other things that Parkinson's is characteristics with, it's heart rate variability, depression, and sleep. There are no currently any working systems for depression and sleep. There's a lot of ongoing work, but we're going to try and convince you that for gait and tremor, we could use some basic biomedical signal processing, embedded in graphical models, and maybe try and do the job. So in terms of what Parkinson's patients feel like, for their number one problem, what they complain about in studies is tremor. So this is what worries them the most. Gait worries the doctors the most, and tremor worries the patients the most. And the second one is slowness of movement, which is essentially gait problems. And then the third most common symptom is, most worrisome symptom is the fatigue tremor. Sorry, did I miss this now? So first we're going to talk about how we did our modeling for capturing quantitative and qualitative markers for gait episodes. So essentially the punchline is variation in the free living of gait data, it's huge. So the way you walk when you're with your partner, with your caretaker, with your daughter at home, outside, with guide or without, or in the garden is fairly rich. So there's a huge heterogeneity in the data, and you're not going to be able to label almost none of it. We do know, though, what are the features of the gait, the statistical features of walking, which are most important in the lab. So our goal is to somehow incorporate these features, which are most important in the lab, but potentially indirectly, so that we can account for this heterogeneity that we're observing in free living. So the four most common features are the so-called total power. So with those with above signal processing background, this is just you measure the spectrum from 0.5 to 10 hertz. The height of the dominant peak. There is cadence, which is a little bit has an opposite effect, weaker effect before and after medication, and the width of the dominant peak. But by far, what we can say is definitely after medication, you have lower power in your gait if everything is normal. And if you have higher power in your gait, it means you have sign symptoms. Same goes for height of the dominant peak and less for cadence and the others. Now, let's have a look at how example accelerometer data looks like for a visit of a Parkinson's patient. So you're looking at 5 hours of data where you have the main useful information is over here and over here with some throughout. So this is your 10-15 minute outdoors walking. This is how it looks like before you take your medication. Then you have a bunch of free living activities, some of which are very similar. And then you have some after medication walking, which sometimes has a clear, better energy, sometimes it doesn't. Now, just within this 5 hour visit, our statistical algorithm is going to detect more than 5 different clusters of very different gait. And all of this is walking with different purposes throughout different times of the day. So you get more than 5 types of different walking just for a single person with Parkinson's throughout the day. And when you increase the number of the patients, you get even more clusters. And then when you start looking at the per second diagnosis of their gait for 2 years, you can imagine that we're talking about tens of thousands of clusters of potential moving patterns. But then the question is, how do you know, how do you try and guess, and how do you try and infer how many of these different variability, how many of these gait patterns occur in free living? And why is it statistically important? So let's have a look at a very simple toy example where we have walking from 2 types. So this is the red one is one type of walking, and then the blue one is another type, real walking from the same person. If what traditional machine learning would do is we would say, well, this data is approximately stationary, and then we would compute the power spectral density over this 20-second window. And then we're going to try and look at some feature of the power spectral density that tells us something useful about Parkinson's disease. Now, the problem with that is that you do the 20-second PSD over this, and you get the orange, the purple power spectral density. So you could see that most of the characteristics of the power spectral density are average between the red and the blue. And most of what you can say about this person compared to another Parkinson's person or a non-Parkinson's person is essentially lost in the detail, and it's like you have a very poor quality data. Now, what a good algorithm should do, or at least an algorithm that we desire, is going to be an algorithm that's going to automatically, from the raw time series, detect when different stationarities start and stop, so that you can go and estimate the power spectral density of the red walking and the blue walking separately, so that you can identify that these are 2 different walking patterns. One with this power spectral density, which is characterized for more slower, less energetic walking, and then the blue one, which is more full of power and full of energy. Now, how do you do this? You can't really do this in the spectral domain, so you need to do spectral analysis in the time domain. What is the simplest way of doing this is by doing autoregressive processes. So the way we're going to try and approach this is we're going to construct these autoregressive processes of high order. So their order needs to cover a couple of seconds of data. So we might be talking about autoregressive process of order 100, which is very sparse because it doesn't have that much spectral resolution, as you can see. Gait has at most few harmonics that are non-zero. So we're going to be placing some new types of some sparse priors on the error coefficients. And we're going to try and embed this in a hidden Markov model so that the hidden Markov model can try and learn for us when do different segments start and stop. So how does this compare to traditional window-based activity recognition, which is being done by both companies and academia quite often? Well, traditional perfect lab-based data, it works very well because you have the perfect activity, you go and estimate some windows. In the lab, these activities almost always stationary for the majority of the time. You estimate your features, and then you try not to worry about the cursive dimensionality and the short training times. You ignore the Gibbs phenomena and all the spectral noises that you're introducing, and you train your black box classifier, most commonly random forest, but nowadays also some advanced deep learning classifiers. Instead, what we're doing by adopting hidden Markov models is getting some free living passive monitoring data, and we're learning, instead of doing equal size overlapping or non-overlapping windows, we essentially learn where stationary segments start and stop and which stationary segments can be merged so that we have a better spectral resolutions on the things that matter for us. So we're going to do this using Bayesian machine learning approach, the switching autoregressive version of a statistical autoregressive model, switching autoregressive model. And the aim is going to be both accurate time localization and accurate high frequency resolution. And it's going to be, we're also going to be inherent to overfitting. I'm not going to have time to talk about it, but please interrupt me afterwards to talk about how we do that and rigorously model uncertainty about the decision process. So the formal architecture is a Bayesian nonparametric hidden Markov model, where we, depending on if we ignore all contextual information, we just have a plain HMM where a hierarchical Dirichlet process models the transition matrix of the hidden Markov model. And theta here are our parameters of the symptom that we're looking for. So for the first example, these are the sparse autocorrelation coefficients of gait in free living. But for tremor modeling, theta is actually parameters of approximate Gaussian processes because we have some nonlinear time series analysis there. And theta in principle could be anything that for which you have appropriate base measure. Now, in a less standard process, we're going to see later on, this trivial construct might not work well enough, and we might start thinking about how do we include contextual variables that affect the latent dynamics of this process. So how does it work when it's all implemented and all applied to free living data? So we specify a generative model, which is particularly useful for gait. So from the sorry, this my slides blocked. So from this picture, we motivated what gait looks like in the spectral domain. Yeah, sorry. So hopefully you remember the power spectral plot of the gait. So based on, we know there is biomedical evidence that information about the gait is contained up to 10 Hertz sampling frequency. So even if you have a higher sampling frequency, it's not going to tell you anything useful about walking, at least what doctors say. So then we design we fix the dimensionality of the autoregressive process so that we can capture frequency information to 10 Hertz. And then we deploy a hidden Markov model, which can automatically learn how many different types of walking are there occurring. Now you're going to say, okay, but there are probably a finite number of walking patterns. Why do we need the nonparametric component? Well, the truth is that this problem that we discussed at the beginning, that we train tools which are trained on about 100 patients, but tested on, say, 65,000. Now, a Bayesian nonparametrics approach allows to initially start off with a small number of gait patterns when we train them on small number of patients in the lab. And as we grow the number out of sample, the number of people on which we deploy the platform, automatically more and more clusters of non-stationary or stationary, depending on your emission mechanism, gait subtypes are being created. And then we have a map of which of these subtypes of gait and non-gait activities are actually useful for Parkinson's disease. So to quantify our assumptions, we quantify our assumptions of gait in a single probabilistic model, and we go about training them using different algorithms, mostly MCMC. We design an interpretable segmentation model which identifies fluctuations of different gait-like patterns. So you might ask, okay, what if there is like a periodic activity very close to gait? So this is actually filtered at the second stage. So the first stage is unsupervised modeling of the gait, whereas at the second stage, we do the causal analysis, and when we look at contextual factors and metadata, which might help you identify what it's non-gait. So if it's something that it's very periodic, but it occurs after stress, it's more likely to be tremor. If it's something that happens always in the same time of the day, in the morning, with a high frequency, it might be brushing of teeth and things like that. And we incorporate domain-informed interpretation of the different gait states. So what does the ready system essentially look like? So if we look at about 7 minutes of gait for a patient who's responsive to medication, here we see that the majority of the time he walks with this sort of like red cluster, which has a particular spectral energy that aligns with spectral characteristics that aligns with bad gait. And after he takes the medication, he or she, they get better, and then they don't all walk well after medication, but most of the time we see this other cluster of gait, which is with patterns which are associated with what we expect is better gait. Now you're gonna say, well, what about people that don't respond to medication? Well, they also walk differently, as you might imagine. I mean, some people walk slower, some people walk faster, depending on the time of day, things change. But we have our model for mapping the interpretation of the clusters of gait tells us, well, look, here you observe two different patterns iterating throughout time, and they're not medication induced. Whereas in the first scenario, we train the model successfully to recognize medication-induced fluctuations and clusters. Now we tested this first against traditional machine learning benchmarks and black box benchmarks as well, to see how well we can recognize gait using probabilistic modeling, nonparametric unsupervised probabilistic model, which sort of like maps, is designed to recognize gait-like activities. And we saw that we are on par, if not a bit better, than majority of the currently adopted systems, with the advantage that our system does not need to threshold adjustment or parameter adjustment whenever it's tested on different data sets. So the first subset of methods here, you can see this poor sensitivity is because they're trained on a set of 100 patients, and when deployed on another set of patients, they do bad if it's from another study. Whereas this is if these methods are trained on the same study, that yes, they do very well, but this is assuming that every time you redeploy a system for detection of Parkinson's disease, you'll be able to retrain it on the newly collected data, which is not the case. We want to train once and have the model follow some mathematical principles to do well. Now, next we were wondering, okay, is what we're doing, is it useful? Can it predict medication-induced fluctuations? And bear in mind, to give you a bit of perspective, out of 25 patients, only 17 get any effect from medication. The other 8, they're either younger or not responsive to levodopa. So at best, we expect 70 to 80% accuracy in predicting medication-induced fluctuations, because the others don't have it at all. And we compare how well would we do in detecting the effect of medication with such technology if we use annotated gait, which means that someone with a camera looked and said what are the periods of the time of the day that we need to look at to say if someone has Parkinson's disease or not. And alternatively, we looked at predicted gait, which is our probabilistic model, identifies different gait patterns, the causal map recognizes which are the useful clusters, and then we essentially use these. And you can see that we do as good as the human annotator, if not a little bit better in some situations, suggesting that indeed the probabilistic model of gait has captured the statistical features which the annotator is looking for, if not a bit more. Now, how well does this work beyond the single 25 patients on these couple of hours is the question. So once you go into continuous monitoring, where people might forget their dose, medication dose, they might forget it but not get symptoms, and we have like essentially it's a lot more difficult to design an app that notifies you when medication is being taken or not. We see a significant drop. So on the same cohort, same people, you could see that so smartphone gives you about 75% accuracy, 76 if you use lower back data, but for smartphone it's 75% accuracy in detecting whether a gait has taken place before or after medication. So whether someone remembered to take their levodopa or not. And you can see that this does drop to 65% when you look at continuous periods of over 2 weeks. But this is expected because in the first phase, we told people not to take medication whole night. So your off medication phase is sort of obvious because this is 15-hour delay in you forgetting to take your medication. In the continuous 2-week monitoring, we get people forgetting to take their medication with 15 minutes to 45 minutes, 2 hours or something like that. It's very rarely that drastic. So, but it's still statistically significant as you can see, which has managed to convince some regulatory bodies to look into it. Now, we also done validation. It's always a good practice to sort of evaluate on additional studies, additional data, which has nothing to do with the data you trained. So we've done evaluation on wrist-worn gait detection with Tel Aviv Medical Center, which is completely different data. It's a different device as well. It's an Apple Watch. We actually managed to get higher accuracy than us from our own algorithms, which was nice. And then we've done also additional evaluation on in Germany on additional study where you can see sort of like what the tool outputs. Obviously, this is designed for medical experts rather than statisticians, so it's a bit vague. I appreciate that. So the idea is to have a clock, 24-hour clock, where different colors indicate different clusters as detected by our model, and same color detects same clusters. So you have bout energy, which is very meaningful for the doctors to look at the detected gait. And colors tell you that essentially you shouldn't be comparing blue bout with yellow bout because the yellow bout it's a different functionally with a different spectrogram type of walking. And you could see that this is a person before they visit their doctor, they exhibit a lot more variation of their gait. This is what the doctors indicate. And then after their medication, this is 1 week of their free living. We see that they exhibit a lot less variation in their symptoms, which suggests that their medication does work, and there's a lot less up and downs in their condition, which was sort of a softer qualitative proof of concept that we needed to establish. So moving towards unsupervised setup, I should highlight some of the open problems that we have is that we have these causal maps designed by the neurologist of all the things that affect things like gait quality features. So whenever you try to train a machine learning algorithm, and hopefully that's the wrong crowd to preach this to, but if you do try to train a black box classifier, you're essentially focusing on isolating this link of using like gait features to try and predict on and off of the medication. And you're ignoring the whole causal structure of the graph. Now, the problem is that majority of the time you don't have access to all of this information. We tend to know when the moment of medication intake is because your GP has this information. Other things that influence on and off, we don't know, and we rarely know some of these other factors as well. So the reason why nonparametric probabilistic models are nice for this sort of applications is because directly from the features, they can detect statistical fluctuation. And now the statistical fluctuation later on can be hypothesized whether it attributes to some of these links, cause-effect links that you care about, or others that you don't. Now, to give you an example, I thought I can pull out a visualization of the environment factor, which we know very well what your environment is, but there are no existing good probabilistic structures, at least we haven't figured out, for incorporating environment. So this is how 2 weeks look like for a patient with Parkinson's, where you're seeing color is the different types of day for the person walking around their house. The yellow circles around the patient's homes. So this is all relative locations, so that we can legally transfer data across EU, and different groups can look at it. And you can see bigger bubbles for bigger sort of like gait bouts or more energetic gaits that we identify. Now, the immediate thing you see if you zoom in is that whenever you're around the house, sorry, I can't zoom in because my browser got stuck, but hopefully you could see that most of the bouts that you exhibit around the house, so they're detected with our hidden Markov model, they're bigger. And this is because when you're around your house, maybe you walk better. But in addition to that, and there is a medical precedent for that because you're more confident around areas that you know. But at the same time, you could see that they're yellow, which means that they're all around the same time of day, which is around 8 o'clock. And now this is at the same time that patients actually take their medication intake. So what that means, and what we've hopefully managed to demonstrate to neurologists, is that by simply collecting accelerometer data and a couple of other wearable data characteristics, certainly that's what Apples and others that are advertising is sufficient to predict medication-induced fluctuations. Actually, maybe you're just predicting environmental factors such as, are you close to your home or are you not? And there's no ways for us to decompose the two effects unless we have information both on environment and on the accelerometer data and on the medication-induced fluctuations. I'll try to go back to, I have just 2 more slides. So we've managed to also show this numerically. We've mostly been able to show that there is a correlation between location and disease and our ability to predict the disease. So here we're like the things to emphasize is that if you use location features and time of day, you can predict statistically significantly. You could predict. So here we're trying to predict the gait energy fluctuation. So you don't hope for R square of 1 because obviously there's a lot of other things that affect your gait energy. But you could see that this is if you use location, you get a lot more explained information that if you just use where was it gait characteristics. When you add on location features and medication, time of medication, then it's quite useful. But if you just look at time of medication, which is ideally what Smart Health used to hypothesize, is that if it's mostly the time from medication that explains your statistical fluctuations in the gait energy, you could see that this is not true. It's simply not true. And you probably might know that this is just due to the fact of gait energy is a continuous variable that has a lot of things affecting it, whereas there is no, when we say time from medication, there's not really a convenient way that you're going to encode it, which is going to explain a large portion of the variation with gait. But nevertheless, clinical trials try to see this single measure being the highest, which is a big bottleneck. So some of the open problems that there remain open, and if people have ideas, it would be great to hear about it, is that identifying reliable models which integrate the effect of different contextual factors for monitoring gait. It's hard, and it needs to be done mostly by people, not by automated machine learning paradigms. It requires discretizing location features in an appropriate way. How do you encode the GPS trajectory? like some of the people in the crowd might have more experience, but this would be like graphical models for continuous smooth processes, capturing effects of other symptoms. So I showed you gait, we've done tremor, but we're currently looking at ways of doing heart rate variability and other things, which are a bit more difficult. And how do we validate on multiple large-scale unsupervised cohorts? How do we train these algorithms in a way where we can account for model misspecification and they can perform robustly out of sample? I didn't talk about this. We have some ways of doing that. There are sort of like new ways of doing likelihood, alternatives to likelihood tempering. But yeah, I'd love to talk about it some other time probably. So I don't, in the interest of time, I'll just skip through the tremor. It's pretty much more or less this is the same. It's just we've changed our model now to nonlinear time series model. So essentially the question is, what if you're trying to detect non-stationary time series fluctuations? So essentially you could think of it as having nonlinear autoregressive processes. And there are two good ways that we've evaluated and implemented for doing this. One is using splines for nonlinear autoregressive processes. The other one is using sparse Gaussian processes, which are, again, embedded in a hidden Markov model. Probably just spending a minute on this, since I'm writing my senior investigator on this idea. But like one of the open problem is how do you look for different time scale events? So in walking and in tremor, it's sort of easy because you know that things on a time scale of a couple of seconds, so order 1 to 30, hidden Markov models can sort of like predict the fluctuation in the next couple of seconds. But when you look at longitudinal studies, a change that occurs in a symptom right now might be due to Markovian dependence that has happened last second, last minute, last day, or a continuous behavior over the last 6 months of you not leaving the house. So how do you then design a variable order sequential model? Now you could do something like a overcomplete hidden Markov model, but training these has severe limitations. So there's essentially, I'll be looking forward to studying how can we phrase this in a way that it's solvable. I think with this I'll conclude. Again, sorry for the change in topic a little bit, and sorry for really skimming on a lot of quite technical details and presenting only the applied bit. So the conclusion is that essentially model-based tools allow us to formally link in-lab digital health predictive performance with free-living digital endpoints, which is a big goal. Symptom prediction is rarely binary, and accounting for heterogeneity is central to achieving application robustness. But it's difficult. It's difficult training these discrete latent variable models with complex emission processes. If you have ideas or you want to know more, of course, get in touch. You can find out some of the code on my website, which is super ugly, but I'm not a developer. And here's some of the future directions that I'll be like trying to study, which are a bit more technical than what I showed. So we're going to be looking at how can we extend this to longitudinal studies? How do we shift from purely predictive focus and develop more qualitative capability? And also, how do we do things like scalable and robust inference of big Bayesian nonparametric Markov models and other structures?